So this video will help us to understand the moment of a force using vector formulation. And the first thing we need to do is do a quick review of the cross product. So if you can recall, if I have two vectors, in this case A and B, and they're shown in the XY plane, if I cross them, I will get vector C. The magnitude is the product of A and B vectors A and B and the angle between their tails. And in order to get our direction, because remember a vector has magnitude and direction, we will look to see that the vector has a directional that's perpendicular to the plane containing A and B. So if this two vectors A and B are in the XY plane, that would make sense that vector C would be perpendicular along the z-axis. And we would use our right-hand thumb rule. So, of course, there's our thumb, our hand, and our wrist. So going from vector A to vector B, we can see that that would be a positive notation. So using the cumulative law, it's not valid. A cross B is not equal to B cross A. So look at the figures that we have here. Again, looking at vector C, vector A and B are in the XY plane. Crossing them will give us a positive if we're going from A to B. But if we're going from B to A, our right hand thumb rule, our thumb would be pointing down, which would be B to A, which is going to give us a negative vector C. And looking at our Cartesian vector formulation of the cross product, you can see up here that I've done, what we've got is the ijk in a clockwise is negative and counterclockwise is positive. So if I cross I and j, I will get k, which is positive. If I cross I and k, I get j, which is negative, and so forth. So if you can see I cross I is 0, j cross j is 0, k cross k is 0. We can also look at it set up as so, where vector A and vector B, we're looking at the cross product of the two. When I'm looking for I don't worry about the I, the j and k, and I don't worry about the ax and bx. I start off with ay, go to bz, and I'm going to subtract az from by. When looking at j, I am taking away the I and the k, and ay and by, start off with ax, cross to bz, up to az. Again, remember when we come back, we are subtracting, so it'll be minus az times bx. And I left this little note here. Always remember to add the negative sign when you're doing our j component. And then our k component, we're using ax, by. Again, we're coming this way, so we got our negative ay and bx. So this would give you a cross b would be our I component, which is ay times bz minus az by. Our j component, again, there's our negative, ax bz minus az bx, plus the k component of ax by subtracting the ay bx. Now when we're looking at a moment, and you can note that I have the moment axes located right along there. So I'm going to go ahead and show the line of action of that axis, that vector right there. If I have a force, and I know this distance r, I can find my perpendicular distance, which we could go ahead and then just use our moment about O is equal to the r, which is here, times the force times sine of theta, which is just going to equal the force times r sine theta, which is just going to equal force times distance. Now, looking at this figure here, what we have is again our moment axis. And we have this line of action, we have this force. I'm going to go ahead and draw a line through it there. We've got this force. Now we can use any distance from O, in this case our origin, to the line of action, to the force. We can use any one of these distances. In case that we know the distance of R3, we could use it, and so on. So the moment about O, kind of small, is equal to R1 cross F, which is equal to R2 cross F, which is equal to R3 cross F. And we'll go through a few examples to help us understand what we're talking about there. Another schematic here, if I've got a force out here in our three-dimensional land, draw that a little bit bigger. We got this force acting over here. And this is the axis that we are drawing or computing our moment about, indicated by our yellow line, where our moments at O, we're looking to see counterclockwise is positive. We have our distance R. We can use our setup as we did earlier, where we are taking the moment about the axis, that's what this is, the moment about this axis, which is equal to R, which is our distance, crossing the force. And if you go back and look at the video just a couple minutes ago, we would have the moment about O, which is R cross F, which we would have Ry times Fz minus Rz Fy. That's what we have for I. And so forth. You would have your J component and your K component. And again, don't forget your negative value there. One other thing I'd like to show on this video is the principle of moments. And our principle of moments, if I've got myself a little bit more room here, if I've got some distance, and let's say I've got two forces, one acting here and another one acting like so. We'll call this F1, and the red vector we'll call F2. And given information that we would know, we could draw, which we've done before, it should look familiar, parallelogram law, where we could find our force resultant given this distance r, we could say that the moment about O, this is our origin, is equal to R cross F, which is equal, or I should say the force resultant, which is equal to R cross F1 plus F2, which is equal to R cross F1 plus R cross F2. So in this case, all I'm saying is if we had this issue or this problem where we have two vectors and their tails meet at some point, but we know that distance, R, we can add the two vectors, get our force resultant, cross those to get our moment about O, or we could also just take the moment, which is R cross F1, and then cross it F2 and add those two moments to get our summation of our moment about an axis. All right, thanks for listening.